Okay, let's look at covalent bonds. So Lewis structures show molecular compounds as atoms that are next to each other, and they are sharing electrons in order to make octets for themselves. So let's look at water and chlorine. So if we look at water, there's an oxygen atom. How many valence electrons does oxygen have? 6. So I could draw a Lewis structure for it like that. And then here's a hydrogen atom. How many valence electrons does hydrogen have? 1. It only has 1 electron. And then, because I know what I'm going to do with this, I'm going to put the other one over here. So if this was an ionic compound, then oxygen would have to convince hydrogen to give up its electron. But it doesn't want to do that. And so hydrogen's trying to get oxygen to give up its electron, and it doesn't want to do that either. So what do you do when two people want something, but neither's willing to give it up? You share it, right? So they're like, okay, we can't agree on who's going to get this electron, let's share it. So if we share these 2 electrons, that forms a covalent bond. When oxygen looks at these shared electrons, it counts both of them as belonging to itself. And when hydrogen looks at those electrons, it counts both of them as belonging to itself. So hydrogen's looking at this and saying, I've got 2 electrons. I look like helium. I'm cool. I'm good. Right? Now, oxygen's not quite done yet, because oxygen right now has 7 electrons and it needs 8. So it's going to take this electron here and share it with another hydrogen atom. So making this hydrogen atom very happy. And now the oxygen is also happy. So the oxygen counts 2, 4, 6, 8 electrons. Octet achieved. The hydrogen counts 2, the hydrogen counts 2. Hydrogen is too small to have 8 electrons. Hydrogen's just trying to look like helium with 2 electrons. It's the little kid version of the noble gases. Any questions? Let's look how chlorine might do that. So here we got 2 chlorine atoms. How many valence electrons do chlorine atoms have? 7. So let's put them in here like this. So there's 7 on that one, and 7 on this one. This chlorine atom says, hey, give me that electron so I can be cool. And this one says, no way, give me one of yours so I can be cool. Argument ensues, cut to the end, they decide to share. By sharing, this chlorine says, I've got 8 electrons. And this chlorine says, I've got 8 electrons too. It's more stable energetically, and that's why this forms. This is why chlorine is found as a diatomic element and not as single atoms. Because if you have the single atoms and they come in contact with each other, they're going to pair up because it's better for them. So in these Lewis structures, we have some electrons that are part of a bond, that are being shared. We have some electrons that are not being shared. They're not part of a bond. So we need to learn how to identify those. So these guys right here, they're shared between 2 atoms. Those are bonding electrons. And then over here, bonding electrons, or bonding pairs, right? And then we also have non-bonding pairs. We usually call them lone pairs because they're off alone. So we got a lone pair here, a lone pair there, and a lone pair here. And then this chlorine has 3 lone pairs. This oxygen has 2 lone pairs. Identifying those is going to be important later when we talk about predicting shapes of molecules. Any questions? Yep.
Is it possible to also have double bonds?
Yes, it's also possible to have double bonds and even triple bonds. These guys don't need to do that, so they don't. But we'll get to that. Any other questions? Yeah.
That was a question. Why does the magnesium and nitrogen, why do they have to share?
That's a good question, actually. Why did magnesium and nitrogen not want to share? The magnesium has a low ionization energy, so it's fairly easy for it to give up an electron, and then the nitrogen has a negative electron affinity, and so energy is released when it accepts an electron. And then you have the opposite charges forming. So there's a more scientific explanation, but I'm going to just keep it simple to help us just know what's going on. If we think about this chlorine molecule, we can't convince one of these or the other to give up the electron, right? Because they both want it. When you have magnesium and nitrogen, and the nitrogen says, hey, give me an electron, the magnesium's like, oh, okay, I'm cool with that. Because it's easy for metals to lose electrons. And it's easy for nonmetals to gain electrons. Here, this chlorine would be pretty happy to gain an electron, it just can't find anybody to give one. So it settles for sharing. Does that help? Yeah. So the real explanation is much deeper than that. The way we remember is we just have learned that metals and nonmetals do the ion thing. So we can have more than one electron pair that gets shared. So let's look at what happens with oxygen. So here's O2. And each of these has 6 valence electrons, right? And I put these around in a particular way because of what I want to do with them, not because that's the only correct way. So 2 oxygen atoms, the goal is 8 valence electrons. So they can share an electron here. Do they have 8 valence electrons? No. So they each have another unpaired electron, and they can share that as well. Now, do they have 8 valence electrons? Yes, they do. That's kind of an awkward drawing. So typically we would draw it like this and show those bonds as just lines, and then put the valence electrons out here, and you could stick those really anywhere you wanted. So when we look at this, oxygen says those are my 8 electrons, and the other oxygen says these are my 8 electrons, because something that's shared belongs to both parties, right? So that's called a double bond. So we represent bonds in Lewis theory as a single line. If it helps you to remember, you can think of it as 2 electrons connecting the dots. Those 2 electrons are shared. So let's look at nitrogen. So we got 2 nitrogens. And they each have how many electrons? Valence electrons? 5. So it's in group 5. You can see why I like those group numbers. Makes things like this very easy. So 5 electrons each. So these 2 guys are going to try to get together and satisfy their need for 8 electrons. And share an electron each there. And then they can share over here and share those as well. When they share each 3 electrons, now they've finally gotten to the point where they have an octet each. This nitrogen counts all the shared electrons. 2, 4, 6, 8. I'm good. This one. 2, 4, 6, 8. So this is like me, and that's my husband, and those are our 6 children. It's a triple bond. So Lewis' model predicts why water is stable, H2O, and H3O is not stable. So let's draw Lewis structures for these. So H2O, we've done that before, so I'm going to do that quick here. And then let's look at H3O. Whoops. So if we're going to put another hydrogen here, how are we going to work that? We'd have to share like that. What's the problem with this? How many electrons does the oxygen have? 2, 4, 6, 7, 8, 9. 9 electrons. That's not 8. More isn't better. It's got to be 8. So this is not stable. If it would happen to form, it would unform. It would change into something else right away because that's not stable. It's not good. It's got 9 electrons around the oxygen. That doesn't work. This is good. Oxygen has 8 electrons. Hydrogen is easy to please, happy with a single bond. That's all it needs, just one bond, it's good. Well, what about H3O+? That's the hydronium ion. How could we make this guy that's unstable into hydronium ion? Lose an electron, right? So let's take away that electron. That's going to give this a positive 1 charge. What do you think? Do you think that's stable? Yeah. Because now the oxygen has 2, 4, 6, 8 electrons again. And each of the hydrogens has a duet, and so that's probably stable. And it is. That make sense? Let's look at how we could make H2O2. So each oxygen has 6 valence electrons, and each hydrogen has 1. And so this oxygen could share 1 with that hydrogen, make him happy, and share 1 over here. And then they could share in between. And now this oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. And the hydrogens each have 2, and so that satisfies the octet rule for everybody. And we predict that that's stable. And it is. It's called hydrogen peroxide. Any questions? Yeah.
In the H3O positive, so we have it's not a double bond, it's just a regular bond.
Mm-hmm.
And then below the O, is that also?
It's a regular bond too.
Okay, just like the double.
Yeah.
Okay,
Yeah, so you can put the dots on each end, sort of like the kindergarten version, or you can draw them without the dots. I start out drawing with the dots because it's convenient to illustrate, okay, we're taking this electron from this one from that one, we're connecting them together. And so if we go like that, then it looks more like a single line. Does this model fit with reality? Well, these covalent bonds are highly directional, right? If we go back to this bond is between this hydrogen and this oxygen. It's not shared with anything else, and so it's very directional. So we have discrete molecules in these ionic compounds. The discrete molecules are held together I mean, we know that water exists as a liquid, right? So those discrete water molecules must be held together by something, but the forces that hold them together are much weaker than the covalent bonds. They're weaker than ionic bonds. And so molecular compounds have lower melting points. So here we have an illustration of, I think that's, what is that, pentane? Yeah, pentane. And so we have individual molecules, and within the molecule we have covalent bonds that are very strong. Between two molecules we have some attraction, but that's weak. And so it will have a low melting point.